Good morning, class. This is Sir Alex again for Physics 2, and today we're going to discuss electric potential. So we're going to move on past Gauss's law to discussing about electric potential. So for the lesson for today, I've included some of the goals that I hope you guys will understand at the end of the lesson. First is that we're going to discuss what electric potential energy is, and then we're going to discuss its relationship to electric field, work, and electric potential. We've discussed about electric field before, so I hope you remember those to help you understand its relationship to electric potential energy. And lastly, we're going to discuss what electric potential is and what potential difference is. So let's discuss what electric potential energy is. But before that, let's discuss first or talk about what what is potential energy. So ano ba yung potential energy? Meron tayong tatlong klaseng potential energy that we know. One is elastic. It is usually the one we deal with when we are talking about springs. The other potential energy that we know of is what we call a gravitational potential energy, which is basically when we talk about gravity. And lastly, electrostatic, which is our topic for today. It's a potential energy of a charge when it is inside an electric field. But first, again, what is potential energy? In the context of a gravitational potential energy, a potential energy, usually we call it as, or we write it as PE, or simply U, is basically the energy stored in an object to its position relative to some zero position. So to kind of understand what I mean by potential energy, let's think of a gravity first, and let's use this analogy to understand what potential energy. Imagine that we have an object. It could be a ball, it could be a person, it could be anything with a mass m. And this object is at the distance h or height h from the surface of the Earth. So the potential energy of that object with mass m is basically equals to its mass times the acceleration due to gravity, which is g, times height. So if you notice on that equation that mg is actually a force. In this case, it's a gravitational force. So we can write the potential energy to gravity is equals to the force of gravity times the height. And if you remember, work is basically a force times a distance. In this case that we have right here, you can see that height is basically a distance, right? So if we have a gravitational force and a height, we can think of this as a distance. So basically, this is equals to work. So what we mean by that is basically potential energy is a work necessary to move an object from the surface of the Earth. So in this case, when we think about potential energy, we think of it as moving downwards. It's because the gravitation or the object is being pulled towards the Earth. But I want you guys to think of it this way. It's a work that is necessary to move a object with mass m from the surface of the Earth towards any direction. It could be upward, it can actually even be downwards. Okay, and this force that you have to use in order to move the object is usually equal to the force of a gravity. And in order for it to become work, it has to travel a certain distance. So if we move an object at a certain distance with a force F, that's what we get for work. So basically, a potential energy is equals to work. But if you think about it, uh, the potential energy is actually not absolute. The potential energy of an object on this distance right here, distance h, and its potential energy, let's say at this distance, is actually different. So this is not an absolute value. Same thing here, the potential energy of an object with mass m at this surface or the surface of the Earth is different if it is right here. So actually what we mean when we say the potential energy is equals to work is that it's actually the negative potential energy or change in potential energy is equals to work. Why is it negative? Simply because, or we will discuss that later, why is it negative. Okay, but with that analogy in mind, let's kind of like move to understanding what is electric potential energy. So earlier we were discussing gravitational energy, and we're going to use that analogy to understand what electric potential energy is. So electric potential energy is basically the energy needed to move a charge against an electric field. I want you guys to look at this word against. So if you look at this context right here, imagine this as a charge. It could be a positive charge, or let's think of it as a positive charge. And imagine the surface of the earth as a plate with a negative charge. We know that this positive charge will get attracted to the surface of the earth because of its electric field, because the electric field, if this is negative, is going downwards. And if we have a positive plate right here, all the electric field will be going downwards, and the direction of the force of this charged particle right here would also go downwards. So earlier I said it is against. It's because we are measuring basically the energy that I need to move a charged particle against the electric field. So remember, the electric field is going downwards because our Earth's surface is negative. So the energy I want, or what I'm looking for, is what energy do I need to move a charged particle opposite the direction of the electric field, and that is why we have a negative uh, potential. In here, it's a negative gravitational gravitational potential energy. But here, instead of a gravitational potential energy, we will be discussing a negative electric potential energy. So this is the example I was trying to give earlier. I have two plates, two parallel infinitely large plates, and if they are infinitely large, we can assume that all the electric fields are parallel. And since we have a positive charge plate above and a negative charge plate below, all the electric fields will be pointing downwards. So this purple line right here, purple arrow, we're all pointing downwards, representing our electric field. And let's say we have a positive charge Q naught or Q0, and we know that the electric field will exert a force on a positive charge with a force with the same direction. And because of this force, let's say that this positive charge is at point A, it can move to point B. And when it moves, there's work included. Okay, so but this is not against. So we're going to think of it as, what if I want to move this positive charge from a point B to point A? So there's kind of like an inverse relationship between work and the potential energy, because as my A, or as my Q0 at A goes towards point B, the potential energy decreases. So the potential energy of Q0 at A is actually higher than B. So um, the work basically of a positive charge from its movement from A to B is equals to a negative potential, or it equals to its negative potential electric potential energy. Because it's conservative, the force is equals to negative potential divided by the distance traveled. So this is the change in potential energy divided by the change in distance. And if we, by algebra, we know that F multiplied by the change in distance is equals to negative U. That's how we actually get work is equals to negative delta U, or delta potential energy. So for U here, when I write U, I'm actually talking about electric potential energy, okay? Please do not confuse it as a gravitational or elastic. We're basically just talking about electric potential energy. So I want you guys to remember this. Work done for an object to move from A to B is equals to negative its potential energy here minus its potential energy at the beginning. I want you guys to remember that equation. So the work done for a charged particle to move from point A to point B is basically equals to negative its electric potential energy at its last destination minus its electric potential energy at its beginning destination. So that is work is equals to negative delta U. But since it's negative, we can just transfer the negative sign and we're gonna get the work done by a charge unit to move from A to B is it basically equals to its potential energy at the beginning minus its potential energy at its final destination. And then we know from Coulomb's law that the electric field is actually equals to force, or the electric force divided by Q. So this is the electric force exerted by the charge particle, or the charge unit, exerted by the electric field. And we know that the magnitude of the electric field is equals to the force divided by the charge of our charged body, or the value of the charge. Rearranging it by simple algebra, we will know then that the force is basically equals to the charge multiplied by the magnitude of the electric field. And we can substitute the value of F to the force and found in work equation. So we can say that QE, or here I wrote QE, or EQ. So the charge times the magnitude of the electric field multiplied by a certain distance is equal to the negative delta U, or the potential energy at A minus the potential energy at B. So this is another equation that I want you guys to understand. And lastly, the conservation of mechanical energy is also applicable via work theorem. So we know that the work is equals to delta K. And in something that is quite interesting to note, since we are dealing with a conservative force, this is a conservative force right here. This electric force right here is conservative force. Any kinetic energy is usually equal to negative delta U. So as your kinetic energy increases, your potential energy decreases. So when we say potential energy, it's the energy while an object is not moving. Kinetic energy, it's its energy while it's moving. So meaning its kinetic energy, as it increases, your potential energy decreases. As your potential energy increases, your kinetic energy decreases. So that's just something that interesting that I want you guys to remember. And because this is conservative, we can use work energy theorem to simply say that work is equals to the potential energy at A minus the potential energy B is equals to the kinetic energy its final destination minus its kinetic energy at its beginning. Rearranging this, we can get basically by adding the potential energy and the kinetic energy at the beginning is always equals to its kinetic energy at its final destination plus its potential energy at its final destination. Again, so I want you guys to remember, if the charge is positive, or if a positive charge moves along the direction of the electric field, its U decreases. If it's moving opposite, so if my positive charge is moving opposite the electric field, then my U increases. Hence, again, that's why we have negative electric potential. So let's look at an example. A point charge of 3 nanocoulombs with a mass 4 grams is moved from, we have a distance 1 meter to 1.5 meters. So a point charge, a positive charge with 3 nanocoulombs and its weight is 4 grams, move from 10 meters to 1.5 meters while it's in an electric field with a magnitude of 5 newtons per coulomb, with the same direction as the motion of the charge. So meaning the direction of the electric field and its motion is basically the same. So we discussed earlier, if it's moving at the same direction and it's a positive charge, then the U is decreasing. So the potential energy is decreasing. So we already have that as our clue. So the question that they're asking is A, how much work is done on the charge by the electric force? B, what is the change in the potential energy of the charge? And C, assuming that the charge started from rest, what is its speed at its final destination, or at x is equals to 1.5 meters? So let's write our given. So we have our value of our Q, which is 3 nanocoulombs, which is equals to 3 times 10 raised to negative 9 coulombs. We have the mass of the charge, which is 4 grams, which is equals to 4.0 times 10 raised to negative 3 kilograms. And the magnitude of our electric field is 5 newtons per coulomb. And our distance traveled is our final destination minus our initial destination. So we have 1.5, this is our final destination, minus our first initial destination, or initial distance, is equals to 0.5 meters. So this is the only distance traveled by our charge, 3.0 nanocoulombs. And what are they asking us is how much work was done by the electric field, how much is the change in potential energy, and C, assuming that the initial velocity at this distance right here is 0, what is its final velocity at 1.5, or its final destination? So in order for us to answer that, we have to understand that to measure work and this type of context, we need force times distance. So we have a distance, but we don't have a force. Later, we know how to solve the force because we know how force and electric potential energy and electric fields are related. Next, we're going to measure our delta U, how much kinetic potential energy, not kinetic, how much electric potential energy, how much electric potential energy is changed due to work. And later we're going to have to use the theorem that I mentioned earlier in order for us to solve for the velocity. So let's look at the solution. For A, we are asked for W, but we do not have the value of the force needed to solve work. But we have the magnitude of E and we have the charge of the particle. Hence, we could solve for F using this equation right here. It came from E is equals to force divided by Q. That's your Coulomb's law, remember? Or not that Coulomb's law. Yeah, basically it's Coulomb's law, but it's also one we discussed in electric field. So the magnitude of electric field is basically equals to the force divided by the charge of the particle inside an electric field. So by rearranging the equation, we can get the force is equals to our magnitude of the electric field divided by the charged particle inside the electric field. After solving for F, then we can use the equation work is equals to force times distance to get the value of work. So work is equals to force times distance, and we know that force is equals to the charge multiplied by the magnitude of the electric field multiplied, and then to get work we just have to multiply the distance traveled by the charged body or the charged particle. So we know the charge to be 3.0 times 10 raised to negative 9 coulombs multiplied by the magnitude of electric field multiplied by the distance traveled by the particles. So we get 7.5 times 10 raised to negative 9 joules. And we use joules because we are dealing with work. The value of joules is basically Newton meters. So Newton meters, 1 Newton meters is equals to 1 joule. For B, now that we know how much work is done by the electric field, we can solve for delta U because we know that work is equals to negative change in potential energy. So we just multiply both sides by -1, so we get the change in potential energy is equals to the negative work. So we know that the change in potential energy is negative 7.5 times 10 raised to negative 9 joules. And lastly, using the energy theorem, we know that work is equals to delta K, or change in kinetic energy. And we have for our kinetic energy, we have our final kinetic energy minus our initial kinetic energy. And we know that K is equals to 1/2 mv squared, something that you guys have to remember since physics 1. This is motion. Kinetic energy is equals to 1/2 mv squared. But according to the problem, we have to assume that the initial velocity is 0. So we can remove the initial kinetic energy. So we are left with work is equals to 1/2 mv squared. So we are searching for the velocity at our final destination or final distance. So we rearranging this, we get v is equals to the square root of 2 multiplied by work divided by the mass of the object. So solving for it, we can get that the velocity at 1.5 meter is basically 1.9 times 10 raised to negative 3 meters per second. So that is electric potential energy. So again, electric potential energy is basically the energy needed for a positive charge body to move against the electric field, okay? So that's one thing that I want you guys to remember. Okay, I don't know what happened to this, but yeah, electric potential and then potential difference. So now we're going to talk about electric potential. Electric potential is different when we're talking about electric potential energy. So these are two things. Electric potential and electric potential energy are two different things. And one of the things that I hope is for you guys to understand their difference tonight or today. So basically, electric potential is a physical quantity we get by dividing the electric potential energy by the charge. So we have an equation for that. So this is the potential, electric potential. We can get the value of the electric potential if we have the electric potential energy that we discussed earlier and divide it by the charge of the value of the charge. Also, the electric potential at a point is the work done by E, or by electric field, to move a unit positive charge from infinity to a point. So earlier, the electric potential energy is to move a unit charge particle against the electric field, right? Against the direction of the electric field. But this time, an electric potential is the amount of work done by the electric field to move a unit positive charge from an infinity to any point. So the amount of electric potential at that point done by the electric field is our potential, electric potential. So this equation is V is our electric potential expressed in units volt, so it's actually related to voltage, and U is our electric potential energy, and Q is our charge. I don't know what happened, the animations all disappeared, but hey. While electric potential energy is the energy needed to move a unit charge against the electric field, this could be positive or could be negative. Electric potential at a point, so this time we're not measuring an electric potential of a charge, we are just looking at a point, okay? Electric potential at a point is the work done by the electric field to move unit positive charge from infinity A to that point B, or to that point. Okay. In case, let's say this is not an this infinity is this point right here is not an infinity, then we have an equation that we can use to solve for that. It's basically then it is the potential, it will become a potential difference. Okay, so in case that where point A is not an infinity, then the work done by the electric field to move unit positive charge from point A, again this is not a infinity now, to point B is called potential difference, and it's usually expressed as VAB. So earlier we only have V, right? But since we are talking now about 2 points, not infinity to a point, but we have 2 points, point A and point B, so we're going to have to use VAB. So VAB is equals to a work done for a particle unit positive charge to move from A to B. So that's work because it's moved from A to V divided by its Q. And we know that W work is equals to negative delta U divided by Q. So we know that we have two, since we have 2 points, now we have two potential energy. So the potential difference between the 2 points is basically the potential electric potential energy divided by the charge minus the electric potential energy at A divided by the charge. And if you're gonna look at this one by one, so UQ and UQ means that's only two potential energy. So basically we have, when we're talking about potential difference, we have to have two potential energies. Okay, or not energy, two electric potential. So the electric potential for VB, or for point B, is equals to the sorry. So the electric potential for point B is equals to the electric potential energy of point B at point B divided by Q, and the same thing, the electric potential for point A is equals to the electric potential energy divided by Q. So it means that the potential difference, when we're looking for potential difference, it's basically equals to the electric potential at point A minus the electric potential at point B. So the electric potential at point A minus the electric potential at point B. So to see what I'm talking about, so let's take an example. So let's say a charge of 6 times 10 raised to negative 7 coulombs is transferred from infinity to a point. So we know that we have an infinity and a point, so we're talking only about 1 point. So we're basically not looking at a electric potential difference in potential, right? But we can also use that to still solve for potential electric potential. So if the work done by electric force to do this is 1.2 times 10 raised to negative 5 joules, what is the potential at point B? So what is the electric potential at point B? So we are given the charge, and we are given that the work done by the electric field to move the charge from infinity to point B is equal to 1.2 times 10 raised to negative 5 joules. So what they're asking is, what is the electric potential at B? So the formula is basically this, the one that I showed you earlier, this one, and this one, right? So our VA is not a VA on our sample problem, it's infinity. So it's infinity here. So that's why we have the equation right here. And we can solve for it by substituting the numbers. So we know that the work done is 1.2 times 10 raised to negative 5 joules divided by the value of the charge, which is 6 times 10 raised to negative 7 coulombs, is equals to V at infinity is 0. So I want you guys to always remember that the potential at any infinity is 0 minus what we're looking for, the potential at point B. So basically, the potential at point V is equals to negative 20 volts. Okay, so electric potential and potential difference, we're going to continue. Electric potential could be positive, negative, or zero. As earlier you saw, when you have a initial starting point at infinity, your electric potential is usually zero. But it can be also positive and negative depending on the sign of the charge. What do you mean by that? Near a positive charge, the potential is usually positive. So we're dealing with a point. So example, we have a positive, and this point we're looking at a electric potential. When this electric potential, this red dot right here, is near to a positive charge, then the electric potential for that point is positive. If it is near a negative charge, the electric potential is negative. The electric potential at a point due to a charged particle is, so this time, the electric field is not coming from a plate, but the electric field is coming from a charged particle. Remember, charged particle can also exert electric field. Okay, so the electric potential is equals to the electric potential energy divided by the charge is equals to QED. So we know this from earlier. We know that negative because of work, and work is equals to F times D. So we have QE is equals to Q. We can cancel Q, so we can say the electric potential at a point due to a charged particle is basically the magnitude of the electric field from that charged particle multiplied by the distance of the point that you're looking for and its distance to that charged particle. Furthermore, we know that E is equals to, this is your Coulomb's law, K, Coulomb's constant, Q, R squared. So the magnitude of electric field is also equals to Coulomb's constant multiplied by the charge divided by the distance of the charge. So this, if you guys remember, this is basically what is the magnitude at a point from a charged particle. So for example, let's say this E right here is a charged particle. This is Q right here is a charged particle. For us to know the magnitude at a certain point, so for example, this is our charged particle again, and we're looking for the electric field magnitude to where my red pointer is. So in order for me to measure the electric magnitude here from this charged particle, this is the equation that I want to use. So this is what is the value of the Q and what is the distance between between the Q and the point that I'm looking where that E is. So we can transfer or we can substitute with that and change D, because this is basically the distance between your Q and your point. We can change that to the D to R. So the basically the electric potential is equals to KQR divided by R squared. We can cancel R in the numerator. So the potential energy at a certain point, not potential energy, I keep saying potential energy. The electric potential at a certain point is equals to Coulomb's constant multiplied by the value of the charge divided by the distance from the charge to the point where you are looking for your electric potential. So so this equation right here, your V is your V is basically your electric potential, and K is your Coulomb's constant, Q is your charged particle including the sign this time, and R is the distance of the point from the charge. An electric field from this equation may also be expressed in volt per meter. So because this is the distance, this is meter. And since we're talking about electric potential now, we're looking at volts. So electric field we've been discussing is usually newtons per coulombs, but we can also express this as volt per meters. So a sample problem to us to understand what is happening at what I was talking about. So suppose we have a point charge of -6 times 10 raised to -9 coulombs, and then this charge is 3 meters from point A and it's 5 meters from point B. So we are dealing with 2 points. So imagine that this charge right here is right here, and then it's the first point is 3 meters and the second point is 5 meters. So find the potential at point A and point B. Next, how much work is done by the electric field in moving a 2 nanocoulomb particles from point A to point B? So we were given a Q is equals to -6 times 10 raised to -9 coulombs, and our distance RA, our first distance from, so the first distance from the point and the charge is 3 meters. The second distance, oh my gosh, my typo. Sorry about that, it's supposed to be distance. So the second distance from point B from the charge is 5 meters. So what are they asking us is what is the electric potential at point A and what is the electric potential of point B, and what is the work done by the electric field if we added a 2 nanocoulomb particle near the point charge and that nanoparticle traveled from point A to point B. To measure these, we need this equation right here that we just discussed, and then we're going to also have to use this right here because we're looking for work, how much work is done by the electric field. So solution, since we're trying to look for the electric potential at points A and B at a certain distance from the charge Q, we can just use this. Potential charge at a point is equals to Coulomb's constant multiplied by the charge divided by the distance of the point to the charge. So plugging in the numbers, this is the Coulomb's constant, this is the charge, this is the point charge, divided by the distance of point A and the point charge, which give us negative 18.0 volts. So as you can see, the sign, the charge, the electric potential at point A is negative because it's close to a negative charge. The same thing, VB is equals to Coulomb's constant multiplied by the value of the charge divided by the distance. This is RB, not RA. So the distance between point B and the source charge or point charge. Plugging in the numbers, you get negative 10.8 volts. So for B, we are looking for the work done by the electric field. We have two electric potentials, we know that. Hence, we can use the potential difference. So this is the potential difference. VAB is equals to work divided by Q, and VAB is basically VA minus B. So the work done is equals to the Q, the value of the charge multiplied by the electric potential at point A minus the electric potential at point B. Substituting that, the work done by the electric field is equals to, this is the Q. As you can see, we are not using this because we're asking for the object that moves. So this Q right here is the object that moved. Okay. So 2 nanocoulombs is basically 2 times 10 raised to -9, and then multiply it by the 2 point charge. And the work done by the electric field from that point charge is 1.44 times 10 raised to -8 joules. So that was our lesson for today. And if you guys have any questions or inquiries, please message me. This lesson I know it can get a little confusing, and especially we're not going to have any virtual class earlier today, but I hope you guys can understand the lesson. And if you guys have any questions, feel free to message me anytime. So thank you and have a good day.